Okay, so as I said, we're going to turn our attention now to finding the area underneath curves. Okay, so the setup is pretty simple. We have a function, f of x, defined on a closed interval. Okay, and so again, sometimes we use open intervals. Here we're really going to use a closed interval just for some technical reasons. You don't really need to think too much about it. But the idea is that here is our function that we can plot. So maybe here's a and here's b. So our function will look something like that. And then the question is really simple. In between x equals a and x equals b is a bounded area. So the area is bounded between the graph of the function and the x-axis. Okay? So this is just some area. And our goal is just to figure out what that area is. Now that's going to take a little bit of time to do, but the first thing I want to mention is that if this area is a recognizable geometric shape, then we can apply known formula. Okay, so let's just review a couple situations that can come up. So for a triangle, if we recognize this region, so if we have some special function where actually this region just consists of triangles, like if it's a line or the absolute value function, something like that, we can just use the fact that the area of a triangle is 1/2 base times height. And then if we have maybe a circle, of course we just have pi r squared. So somehow if the graph of a function consists of pieces of circles, so sectors of circles, then we can just use the area of a circle and just divide it up appropriately. And there's some other situations too. So if it's a rectangle, or maybe somehow it consists of rectangles, we can form it by just kind of pasting some rectangles together. Of course, the area of a rectangle is length times width, and etc. I'm not going to sit here and list out all the possible geometric formulas that we may run into, but the point is that in some special cases, we actually can already solve this problem. If we recognize the graph of the function as being the boundary of some geometric shape or some union of geometric shapes, then we can just use our known geometric formulas. Where it really gets interesting is when our function does not fall into one of these categories. Okay, so here's a picture that's going to illustrate kind of our first attempt to solve the general problem of finding the area under a curve. Now here the function h of x is equal to x squared. Okay, so this blue line is the function x squared. And we're interested in this area, bounded between x equals 0 and x equals 1. And then the graph of x squared and the x-axis. Okay, so it's almost a triangular region, but you see that the top side right here is actually curved. And so the initial idea, or the kind of naive thing to do, is approximate the area by rectangles. Okay, so notice here, these rectangles, I've sort of just broken up the region into 4 pieces, or 4 parts. So I've broken up the interval 0 to 1 into 4 parts. So another way to say this is that I have partitioned the interval 0 to 1 into 4 equal parts. Okay, so we have the interval from 0 to 0.25, the interval from 0.25 to 0.5, the interval from 0.5 to 0.75, and then the interval from 0.75 to 1. Okay? And so each one of these parts of my partition, so this word partition simply means that I'm breaking it up, and the union of all of these intervals is the whole interval, and their intersection is empty. Their pairwise intersection is empty. Okay, and so each one of these parts of my partition gives the base of one of these rectangles. And now I used equal parts so that actually each one of these subintervals has the same width. So they're each of just length 1/4, or 0.25. So then now I just need the height of each rectangle. So the base is 0.25 here, and here, and here, and here. But what about the height of each rectangle? Well, here I actually have to make a choice. I have to pick how high I want the rectangle to go up. And here I've actually specified the right endpoint of each subinterval, so 0.25, 0.5, 0.75, and 1 to be the height. So the height here is f of 1. The height here is f of 0.75. The height here is f of 0.5. And then the height here is f of 0.25. Okay, but I could have just as easily used the left endpoint. So for the height of the rectangle, we can use the right endpoint, the left endpoint, the midpoint. So the midpoint would be like this point here. That would give me a different height. Or I could really use any point I want in the subinterval right here to give the height of the rectangle. And it turns out that it's not really going to matter in the long term. All it's really going to do now is that sometimes in specific cases, using the right endpoint, using the left endpoint, or using the midpoint might give a more accurate approximation, or it might give an overestimate or an underestimate, just depending on what the shape of the function is. Okay, but the point is here, to approximate this area, we're going to break it up into rectangles. And of course, here I broke it up into 4 rectangles, but I could have broke it up into more, right? I could have broke it up into 100 rectangles. And of course, the idea is the more rectangles I use, the more accurate the approximation will be. So let's just see actually what this approximate area is. So let's just think, we can make a choice, right? So we can either use the right endpoints, the left endpoints, or the midpoints. So let's see how that goes. Okay, so remember my goal is to approximate the area between the x-axis, the graph of y equals x squared, x equals 0, and x equals 1. Okay, so that region we had before. Now I can use right endpoints, which I'll denote by the capital R. So, and then I'll put a subscript of n. So this is going to be n rectangles, equally spaced rectangles. So that's important. With right endpoints for the height. So I'm going to evaluate the function at the right endpoint to give the height of the rectangle. I can also use what I'll call L sub n, which will be n rectangles with left endpoints. Again, for all of these, they're going to be equally spaced. And then I can also use what I'll call capital M sub n, which is n rectangles with midpoints. So of course, when I say right endpoints, left endpoints, midpoints, that's the point in the subinterval that I'm using. I'm going to evaluate the function there to give the height. Okay, so for our problem, let's just think about what is R for. Okay, so this is going to be, well, it's just going to be, I'm just going to add up the area of each of those rectangles. And the height, I'm going to use the right endpoints. So the width of each one is 0.25. Okay, and then the height of the first rectangle, I'm going to evaluate the function x squared at the right endpoint, which is 0.25 squared. And then the second rectangle has width 0.25. They all have width 0.25. But now I'm going to evaluate the height of the rectangle at, okay, the function evaluated at the right endpoint of the second subinterval. And then I have the third rectangle, and then the last rectangle. Okay, so this is just rectangle 1, rectangle 2, rectangle 3, rectangle 4 in that last picture that we saw. So that was an illustration of R4. And so what do we get here? Well, you just do it, and you get 0.4685. Okay, So that is the approximation using n equally spaced rectangles with right endpoints for the height of the area between the x-axis, y equals x squared, x equals 0, and x equals 1. So we can also look at L4, and now L4 is going to be almost exactly the same thing, but instead of evaluating the function y equals x squared at the right endpoints, we're going to evaluate it at the left endpoints. But the width is going to be the same. But now instead of 0.25, the right endpoint of the first rectangle, I'm going to use the left endpoint, which is 0. So 0 squared, and then now the left endpoint of the second rectangle is 0.25. The left endpoint of the third rectangle is 0.5. And then finally, the left endpoint of the fourth rectangle is 0.75. And we compute this, and we get 0.21875. Okay, so we get a lower estimate of the area. And so actually from the picture, we can see that our 4 is going to be an overestimate, right? The rectangles hang over, whereas L4 is going to be an underestimate, because if you draw in the rectangles using the left endpoint, you'll be underneath the area. So typically a better approximation is to use the midpoints, because it'll somehow average using the right endpoint and the left endpoint. So it'll give a better approximation, typically. So using the midpoint, again, the width of each of the rectangles is 0.25. That's not going to change. But now we're going to evaluate the function x squared at the midpoint. So the midpoint of the first subinterval is 0.125. So I got that just by averaging 0 and 0.25, the left and right endpoints. So that right in the middle is 0.125. And then for the second subinterval between 0.25 and 0.5, I do the same thing. I just find the midpoint. That's going to be 0.375. And then for the third subinterval, we'll have 0.625. And then finally, we'll have 0.875. Okay, and then what do we get when we compute this? We get 0.32815. So you see that the approximation using the midpoint of the interval is somehow in between the right, using the right endpoints, which we said is an overestimate, and using the left endpoints, which is an underestimate. And in fact, what we'll see in just a second is that the actual area underneath the curve of y equals x squared between 0 and 1 is 1/3. Okay, so notice that M4 using the midpoints is pretty close to 1/3. So it really is a pretty good approximation. Whereas using the right and left endpoints are pretty far off. Okay, but that's really just a case of using relatively few rectangles. All right, so we're interested in getting better and better approximations. So to get a better approximation, what do we do? Well, we want to use more rectangles. And I'll say that as we use more and more rectangles, it's going to become irrelevant whether we use the left endpoint, the right endpoint, or the midpoint. And so just to be consistent, let's just use Rn. Okay, so the same question. We want to find the area bounded between the function y equals x squared and the x-axis between x equals 0 and x equals 1. Okay, so let's just write down what R sub n is in general. So what do? Well, we're going to use n rectangles. Using n rectangles, and of course, these are going to be equally spaced. Otherwise, things get unnecessarily complicated. So using n rectangles of width, well, what's the width of each rectangle going to be? Well, this is just kind of a geometry question. If I want to partition an interval into n equal parts, well, I'm just going to take the width of the total interval, so the width of this interval is 1, and divide it, literally just divide it by the number of parts I want. Okay, so n rectangles of width 1 over n, and then height. Well, what is the height of each rectangle going to be? Well, I need to think about what are the right endpoints of each subinterval. Well, if I start breaking it up, here's 0 all the way to 1. Well, I'm going to have 1 over n, and then my next right endpoint is going to be 2 over n, and then my next endpoint is going to be 3 over n, all the way. My second to last one is going to be n minus 1 over n, and then my last one is 1, which I can think about is n over n. Okay, so the height is going to be I over n squared. Okay, so I'm just going to pick one of these right endpoints for the ith rectangle. Okay, so where I is between, it's starting at 1, so between 1 and n, we have R sub n equals, well, we're going to have 1 over n, which is going to be the width of each rectangle. And so I can actually just factor out that 1 over n. So that's just, each term is going to have a factor of 1 over n. That's the base of each rectangle. And then the height of each rectangle is going to be I squared over n squared, but that means each height has a factor of 1 over n squared, so I can factor that out, so I have 1 over n cubed, and then I just have 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. Okay, so all I did, really, if I expand all this out, what I'm saying, this is 1 over n times 1 over n squared plus 1 over n times 2 squared over n squared plus 1 over n times 3 squared over n squared. Okay, that's the same thing. I just did a little bit of simplification. So I just factored out all of the common terms. Each term has a factor of 1 over n cubed. And again, this is just base times height, base times height, base times height for each of the rectangles. And I'm just using the right endpoint to evaluate the function to get the height. Well, it turns out, so we can show, which we will show later, I promise, that 1 squared plus 2 squared plus 3 squared plus all the way up to n squared actually has a closed formula. So what it is n times n plus 1 times 2n plus 1 all over 6. Okay, so actually, it's not that hard, at least for this simple function y equals x squared, to give a nice formula for the approximation of approximating the area using n rectangles equally spaced of width 1 over n, and then height given by the function evaluated at the right endpoint, which is just I over n, that quantity squared. But this is really, really nice, because what we're going to do next is think about what happens when n goes to infinity, or in other words, when we use more and more and more and more rectangles. Alrighty, so we're going to use a lot of rectangles to approximate and eventually, hopefully, find the exact value of the area between x equals 0 and x equals 1, bounded between y equals x squared and the x-axis. Okay, so recall what we're doing is we're breaking this up into a bunch of really thin rectangles like this. And now, just to be consistent, we're using the right endpoint to give the height of each of these rectangles. And you see that as we use more and more rectangles, so this is n rectangles, where n here I just want to think about as a very large number. So the width is 1 over n. The height of the ith rectangle is I over n squared. Okay, so we actually know what this area is of all of these rectangles added together. So r sub n, as we just saw, is 1 over n cubed times n plus 1 times 2n plus 1 all over 6. Okay, so that's the area of the sum of all of these rectangles, which, as you can see, is getting very, very close to the actual area underneath the curve of y equals x squared. And so we expect that the area is the limit is n goes to infinity. Okay, so basically as we use an arbitrary amount of rectangles, so essentially infinitely many rectangles, Now each one of those rectangles will be infinitesimally skinny. Infinitesimal is just kind of the opposite of infinite, just very, very small. So we expect the area is the limit as n goes to infinity of r sub n. And that's actually true. Okay, so we have not justified that, but I think the justification, or at least the intuition, is clear. As we use more and more and more rectangles that are getting skinnier and skinnier and skinnier, they're better approximating the area in each little kind of small slice, if you will, of the actual area. Okay? And now it's just kind of a pretty elementary exercise to take the limit of this function as n goes to infinity. Notice that this is a rational function, right? So if we factor out the highest factor of n on the top and the highest factor of n on the bottom, then we're going to have basically something like 2n cubed over 6n cubed times 1 plus some stuff that's going to 0 over 1 plus some stuff that's going to 0. So the interesting thing is just kind of the leading terms, or if you will, the limit should be approaching the ratio of the leading coefficients, right? In other words, we have a horizontal asymptote at 1/3. So that means the limit as n goes to infinity is approaching 1/3. And so in fact, 1/3 is the area underneath the graph of y equals x squared between x equals 0 and x equals 1. So that's the idea behind actually computing exactly the area underneath the graph of a function. You just break it up into small pieces and small rectangles. And in the limit, it's not really going to matter whether you use right endpoints or left endpoints or midpoints, doesn't matter. But you take the limit and it should be approaching the area underneath the curve. Okay, so let's talk about the general setup. So the area under, let's say it this way, the area bounded between a function f of x and the y-axis on some closed interval, a to b. And so again, the picture just looks like this. That's what we're looking for right there. The area bounded between f of x and the y-axis. Now, we're going to make a technical assumption about f of x, that it is continuous. And now if it's continuous, this will all make sense on, kind of a very technical level. So the area bounded between this continuous function, f of x, and the y-axis on this closed interval AB. That's our goal. Well, the first thing to do is partition AB into n equal subintervals. Each of length and here I'll just use some notation. I'll say delta x is the width of each of those small subintervals, which will be the width of each rectangle. should be the length of the interval, so b minus a over n. And so what we have are a collection of subintervals that look like this: x sub I minus 1 to xi. So here I is going to go from 1 to n, so this is my just collection of subintervals. And now what is xi? So x sub I is going to be a, so the left endpoint of the interval, plus I times delta x. Okay, and you can verify that this is the case. So so I'm starting at a, and then each part, I'm just going to add delta x. Okay, so if I want kind of the ith right endpoint in this case, I'm just going to add delta x I times. Okay, not too hard to see. Okay, and then what's next? So we want to evaluate f of x at the ith right endpoint. So the ith rectangle has area, well, it's going to have area what? Delta x base times the height, which the height is f of a plus delta x times I. Okay? And now this is for R sub n. What about if we wanted L sub n? Well, for L sub n, we just want to evaluate not at the ith right endpoint, but the left right endpoint. So that's x sub I minus 1. So that's going to be a plus delta x times I minus 1. This is for L sub n. And then for the midpoint, if we wanted to do that, it's just delta x times f of, and I'll just write it this way, whatever x sub I minus 1 is, plus x sub I over 2. So it's the average of the left endpoint and the right endpoint. Okay? So we're saying right endpoint, and if we're just going for the exact value and taking a limit, it's really not going to matter, so we might as well just use the right endpoint. But we can also just do approximations by the left endpoint and the midpoint. So the final step to find exact area is just going to be delta x times f of a plus delta x plus f of a plus 2 delta x plus plus f of b. So this is R sub n, but we're going to take the limit as n goes to infinity. Okay, so that's going to be the exact area. Now we would get the same thing if we did the left endpoint or the midpoint, but it doesn't matter. Okay, so that's the general setup. You have a continuous function, you want the area, you partition the interval you're interested in into n subintervals, each of length delta x, The right endpoint of each one is a plus I times delta x. And then we're just going to evaluate f of x at the ith right endpoint to get the height. And then to get the exact area, we just take the limit of the sum of all the rectangles as n goes to infinity. So that's the idea. Pretty simple, pretty naive. Again, we're just using this machinery that we built up at the beginning of the course about limits to really give an answer to a question that we would not be able to really solve otherwise. Alrighty, so we want to find the area beneath the graph of the following functions on the specified intervals. Okay, so here we have f of x, square root of 1 minus x squared, between x equals 0 and x equals 1. Now this is a very important example because based on our previous conversation about finding areas, your temptation might be to start breaking this up into small pieces, adding them up, and then taking a limit as the number of rectangles we're using is going to infinity. But remember the first thing we talked about is that sometimes you can actually recognize the area as being part of a geometric shape. And so notice that this area is 1/4 of a circle of radius 1. So don't do a lot of work. Just use your area formula for a circle. So the area is just going to be 1/4 the area of a circle of radius 1, which is pi r squared, but of course 1 squared is just 1. So the area is actually just 1/4 pi. Okay, so easy as it gets there. I mean, we really don't need to do anything crazy because we already know the area of a circle and we're just using that to our advantage and recognizing that this function really is just a quarter of a circle, right? Because if I say y is f of x, then this is just the positive square root looking at the equation y squared plus x squared equals 1. Okay, similar situation here. Now, the first thing you might be tempted to do is just to break this up into small pieces and then add up the rectangles, the area of the approximating rectangles, take the limit, but maybe this one's a little bit clearer. This is just area of a triangle. This is just the area of a triangle. So we call this one triangle 1, triangle 2. So the total area is just the area of triangle 1 plus the area of triangle 2. So the area of triangle 1 is 1/2 base times height. This has a base 1 and a height of 1, so it's just 1/2. And then let's see, so 1/2 base times height here, the base is 2 and the height is 2, so just 1/2 times 2 times 2. So this is 1/2 plus 2, which is 5/2 or 2.5. All right, so the area is just 2.5. And again, we just found this by recognizing that the graph of this function was just two rectangles. So we just took the area of the area was two triangles. So we just took the area of those two triangles and added them up, and that gave us the total area, 2.5. Okay, so we want to approximate the area under this function, 1 over x, on the interval from 1 to 5 using this particular approximation. So remember, R4 means we're going to use 4 equally spaced rectangles, and we're going to evaluate the function at the right endpoint. So let's just draw, first of all, this interval so we can really see what's going on. So here's 1 and here's 5. And now we want to partition the interval into 4 equally spaced subintervals. Okay, so we need, therefore, 3. You always need one less boundary to separate it into 4 pieces, so we make kind of 3 cuts. And if we look at the width that the base of each rectangle should be, it should be 5 minus 1 over 4. But that's just 1. Okay, so this is really 2, and this is 3, and that's 4. So here we've partitioned the interval 1 to 5 into 4 equally spaced subintervals. And then we want to get our rectangles, so our function 1 over x kind of goes down like that. So to approximate, we want to use the right endpoints. So we'll use this endpoint. Then we'll use this endpoint. Then we use this endpoint. And finally, this endpoint. So notice that I'm just going to evaluate the function here, 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 and here to get the width, to get the height of each rectangle. So now R4 is just going to be base times height, base times height, base times height, base times height. Okay, so this is the first, second, third, fourth rectangle. So we have 1 times, okay, so we need to evaluate the function at 2 plus 1, the width of the second rectangle, times the height will be given by f of 3, and then plus 1. Height of the third rectangle will be f of 4, and then plus 1, base times height. F of 5 gives the height. Okay, so pretty straightforward. This is rectangle 1. This is rectangle 2, the area, that is. This is rectangle 3. And this is rectangle 4. So let's just see what f of 2, f of 3, f of 4, and f of 5 are. Well, it's just going to be 1 over the input. So this is 1 times 1/2, 1 times 1/3, 1 times 1/4, and then finally 1 times 1/5. So if I just add up the area of these 4 rectangles, what do I get? Well, I get 154 over 120. If I just simply do the addition of the fractions, so a little bit more than 1. Maybe about, I don't know, a little bit more than 1.25. Well, you can figure it out. But that's the exact value of the approximated area, okay? So that gives an approximation of the area under this curve, 1 over x, from 1 to 5. Using right endpoints, 4 equally spaced rectangles. So here's just a little bit better picture, computer generated, of what we're finding here. Okay, so remember the approximated area was just the sum of these 4 rectangles, and we got 154 over 120, and you see, I just want to point out that R4 here appears to underestimate the area. And the reason I say that it underestimates the area is because all of these rectangles are kind of strictly contained within the area I'm trying to find. And so we're sort of missing this area, this area, this area, and this area. Okay, so that's kind of the idea. It's good to think about whether or not your approximation is overestimating or underestimating, or whether it looks like it might be pretty good. So there we go. Okay, so again, the instructions are pretty straightforward. We just want to approximate the area underneath this curve from -1 to 2, or bounded between this curve and the x-axis, that is, using M3. Okay, so that's using 3 equally spaced rectangles and then evaluating the functions at the midpoints of those equally spaced intervals to give the height of each rectangle. So if we break up this interval, here's -1 and 2. So notice that the width of each subinterval, if I break it into 3 equal parts, should be 2 minus -1 over 3, but that's again just 1. Okay, so we'll draw 2 ticks to break it into 3 equal parts. This will be 0 and that'll be 1. But now the important thing to remember here, so whatever our function looks like, don't really care. Right now, we'll look at a better picture later, is that I want to evaluate the function at the midpoints of these intervals. Okay, so we evaluate at the midpoint, and that'll be our height of each rectangle. Okay, so what is the midpoint of each of these subintervals? Well, that's not really too hard to see that this is -0.5. If I really wanted to think hard, I could just add these two together, these two endpoints, the left and the right endpoint, and divide them by 2. So this will be 0.5, and this will be 1.5. Okay, but now it's really easy to see what M3 is. M3 will just be 1, so base times the height will be f of -0.5. The area of the second rectangle will be the base, which is also 1, times the height, which is the function evaluated at 0.5, this midpoint. And then the area of the last rectangle will be the base, which is 1, times f evaluated at 1.5. Okay, the midpoint of this subinterval. And at this point, you know, it's fine to just use a calculator. So let's see. It appears let's see, so f of -0.5, so this is just 1 times that. Well, this is going to be, okay, so what is -0.5 cubed? That's going to be, okay, it's going to be negative. 5 cubed is 125, and then we just keep the decimal point there, okay? And then plus 2, so that's the area of the first, and then the area of the second. All right, now this is 0.5 cubed, so that's 0.125 plus 2. And then finally, okay, 1.5 cubed. Well, this is a little bit trickier. So 1.5 squared is 2.25, And then if we multiply by 1.5, what do we get? We get 2, 5, and then 10 would be 12, and then 11, and then let's see, this is 2, 2, 5. We have 5, 7, 3, 3, and then move the decimal point 3 places. So, okay, that's some fun arithmetic. So 3.375 plus 2. So the approximation here, well, now we have a negative 0.125 and a plus 0.125. We have 2 plus 2 plus 2, which is 6, and then we're adding 3.375, so it looks like we get 9.375 for the approximated area. Okay, and that's how it goes for the midpoints. Okay, so here's a graph of this function plotted with the computer, so it's fairly accurate. And then I've just plotted in these approximating rectangles. And, there's not really much you can say here, but notice that because we're using the midpoint of each subinterval here, that kind of on the left, we are actually going to overestimate a little bit, and then on the right of each subinterval, we're going to underestimate. So overestimate, underestimate, overestimate, underestimate. It's kind of hard to compare how much we overestimate or underestimate, but we see that at least, some places we're overestimating and in some places we're underestimating. So our conclusion is that this approximation seems, okay, not being very precise, but it seems to be pretty good. And again, the reason I'm saying that it seems to be pretty good is that we are both overestimating and underestimating in approximately the same amount. I mean, of course, it's very unlikely that it's exactly the same, but it looks pretty good. So that's just a way we can qualitatively analyze the approximation by just looking at the graph geometrically. What does it look like it's doing? All right, so let's look at one more example. In this function, we want to approximate the area bounded between the graph of the function and the x-axis between -2 and 2. And we're going to use L4, which means use 4 equally spaced rectangles and evaluating the height at the left endpoint. So if we look, just kind of a sketch of the interval, we have -2 and 2. And so what is the width of each subinterval going to be? Well, it's going to be 2 minus -2 over 4, which again is 1. Okay, so we'll split this up into 4 pieces. Here's -1, 0, and 1. So our function is something like that. I don't really know exactly what it looks like, but the point is we're going to be using the left endpoints to evaluate the height of each rectangle. Okay, so again, left endpoints. So then L4 should be something like base times height of the first rectangle, so 1 times f of -2, and then base times height, so 1 times f of -1, 1 times f of 0. That's the left endpoint of the third rectangle. And then finally, 1 times f of 1. All right, so f of negative 2, that's going to be 1 over 1 plus 2 squared is 4, so 1/5. And then plus 1 over 1 plus 1, that's 1/2. And then 1 over 1 plus 0, that's 1. And then f of 1, 1 over 1 plus 1 is 1/2. So the approximation should be, well, 1/2 and 1/2. 1 plus 1 is 2, and then 1/5, so that's 2.2. That's our approximation to the area underneath the curve, given by the graph of this function. Okay, so now let's look at a picture and see about how well we did with this approximation. Alrighty, so here we see the graph of f of x, 1 over 1 plus x squared, accurately graphed using a computer. And then we have these rectangles that are approximating the area under the curve. And so again, on the left-hand side, we're definitely underestimating for the first two rectangles, but then the second two rectangles on the right-hand side, we're overestimating. And it really looks like the amount we're underestimating over here is accounted for by the amount we're overestimated over here. Now, certainly not exactly, but it's enough to say that the approximation seems pretty good. It's not obvious to me whether it's an underestimate or an overestimate. So I'm going to say that it seems pretty good based on this picture right here. And something to note is that when a function is increasing, using left endpoints is going to give an underestimate, and when a function is decreasing, using left endpoints is going to give an overestimate. Now, the exact opposite is true when you have a function that is increasing and decreasing using right endpoints. So it's just something to think about. It's a good qualitative question to kind of ask yourself, okay, if a function is increasing and you for sure want an underestimate, then you should use left endpoints or whatever. So it's just something else you can think about when you're doing an approximation.